Okay. Let's see. So let's go over some questions from Unit 1, Module 1, like phase behavior questions. Start with this. Which of the following phase changes absorb energy from the surrounding when they occur? Okay, so just remind us about what's involved here. So, we can think about heating and cooling, right? Okay, if you're heating, then energy is absorbed by the system, okay? And delta E, or the change in energy, will be greater than 0. And if you are cooling, on the other hand, okay, energy is released from the system because we are taking away energy from the system. And then by convention, for this, the change in energy is less than 0 or negative. That's the idea. Now, the question is, which of the following phase changes absorb energy? Okay, that means something like heating. Okay, so if you think about boiling, okay, boiling means we are going from liquid to gas phase. Okay, and when for the liquid to become gas, energy needs to be absorbed by the system. Therefore, this should be one of the answers. And melting, the same case, that means solid becoming the liquid. Again, energy needs to be absorbed. And depositing means gas to solid. For the gas to become solid, we need to either cool it down or remove energy from the system. Okay, and then if that is the case, energy is released from the system, not absorbed. Therefore, that is out. And freezing is liquid to solid. Again, the same thing. We need to remove energy from the system for this to happen. Therefore, energy is released during this process. Okay. One thing to keep in mind, at this point, we haven't talked about this in class yet. What is happening here is the energy absorbed or released as potential energy in this case, okay, during the phase transitions, and that's why the temperature remains constant. We will talk about that a bit later. All right, anyway, the correct answers are boiling and melting. Okay, let's do this one. During the dry cleaning process, the perk or whatever the substance, liquid, gets vaporized. Okay, liquid to gas. We have this screenshot. Okay, so we're talking about liquid to gas phase transition. Which of the following diagrams best represents the change in energy, or delta E, as a function of temperature during this vaporization process? Okay, again, so if you're going from liquid to gas, energy must be absorbed by the system. Therefore, delta E, or the change in energy, must be greater than 0. Okay, it should be positive. Okay, therefore, any answer like option B or D, where you have the change in energy less than 0 or negative, we can eliminate right away. And between A and C, without thinking too much, we can see that we always we have in C, we have this horizontal region, meaning the temperature increases, but the energy does not change. That's what it tells us. But this can never happen. If the temperature changes, energy has to change because the kinetic energy changes with temperature. Okay, therefore option C is out. Therefore, our correct answer must be option A. Just to walk through this answer, okay, you always start reading at delta E equals 0, because at that point we haven't done anything to the system. Okay, the change in energy is 0 initially. At the beginning. Therefore, we're going to start at this point. Okay, and then we increase the temperature. With increase in temperature, energy increases, and then during the phase transition, okay, this should be the liquid to gas phase transition. The temperature does not change, but energy is absorbed by the system still during this process to convert liquid to a gas. And then once everything is converted to gas, then again energy increases with temperature. So this should be the gas phase over here, and this should be liquid phase over here. Okay, so the correct answer is option A. All right, so let's select that. Moving on, which of the following is a good differentiating characteristic for a chemical substance? If it is a differentiating characteristic, it needs to be intensive, meaning the value of the property does not depend on the amount. And also, it needs to be a unique property. Okay, that means it cannot be a system property such as temperature or pressure, because something like temperature or pressure is not unique to a given substance. You can have many different substances at the same temperature. Okay, for that reason, temperature and pressure are not unique properties, therefore you cannot use them. Okay, so volume is an extensive property. That means it depends on the amount. So that is out. Weight, again, or the mass depends on the amount. Therefore, it is an extensive property. Therefore, we cannot use weight. Pressure is an intensive property. That means it does not depend on the amount, but it is not unique to a given substance. Okay, it is a system property. Therefore, pressure is out. You can have like oxygen and nitrogen at the same pressure. Okay, that means that pressure is not unique to a given substance. All right, and on the other hand, we have the solubility in water. Solubility in water, that means amount of substance dissolved in, say, 1 liter of water does not depend on how much substance you have. Okay, for an example, the sugar, solubility of sugar in water, okay, does not depend how much you have because of the way it is defined, because it is always defined per 1 liter of that solvent, right? For that reason, it is an intensive property. And also the solubility of a substance is unique to a given substance. Therefore, we can use solubility as a differentiating characteristic. Okay, moving on. What is true during a phase transition? During a phase transition, I think all of these answers are talking about temperature. What we have observed is we have seen that the temperature does not change during any phase transition. It could be solid to liquid, liquid to gas, or gas to liquid, or solid to gas, or gas to solid. Whatever the phase transition is, temperature does not change. Okay, so the correct answer is temperature of the system. First thing, temperature of the system remains constant during a phase transition. So that's our answer for this. Okay, question 5. Which of the following graphs represents the energy change as a function of temperature in a system where water vapor is cooled down? Okay, we are cooling. Okay, if we are cooling, we know that the delta E, or the change in energy, must be less than 0 or negative. Okay, cool down and transform into liquid water. So we are going from gas to liquid. Anyway, we're cooling down. In other words, delta E must be less than 0. Therefore, any answer with delta E positive, like option A or option D, must be out, because they show that delta E is greater than 0, which cannot be for cooling, for a cooling process. And between B and C, if you look at option C, we come back to B. Okay, we are starting at a lower temperature, and then after cooling, we are ending up at a higher temperature. This does not make sense at all. Okay, if we are cooling, the temperature must decrease, not increase. Okay, but in this case, in option C, the temperature has decreased, because remember, we always start at delta E equals 0. We always start at this point where we have delta E, or the change in energy, is 0, because at the beginning we haven't done anything to the system. Therefore, change in energy is 0. Okay, so we see we have a lower temperature at the beginning, and at the end we have a higher temperature. This cannot happen when we are cooling, so that is out. Therefore, the correct answer must be option B. You can see in option B, we are starting at a higher temperature. Okay, and then we cool, and when we decrease the temperature, energy decreases. And then during the phase transition, this should be the liquid to gas to liquid phase transition, or the boiling point, or the condensation point. the temperature remains constant, but energy keeps decreasing because we are removing energy from the system to convert gas to a liquid. We are decreasing the potential energy. We'll talk about that later. And then again, once everything is converted to liquid, again with temperature, the energy decreases. Okay, so we are going from a higher temperature to a lower temperature during this process. Therefore, B sounds really good. So we can select that. Okay, so we'll select B and moving on. Which of the following are not important features of a differentiating characteristic or differentiating property? Okay, that we can use to detect, identify, and separate chemical substances. Anyway, if it is a differentiating characteristic, number one, it needs to be an intensive property. Number two, it needs to be unique. That means it cannot be temperature or pressure because temperature and pressure are system properties. Okay, so qualitative, quantitative doesn't have anything to do with that. So that is not what we're looking for. It cannot be extensive. It needs to it says not. Which of the following are not important features? Okay, so when it comes to not important features, we know being intensive and unique are important. Therefore, what is not important must be qualitative and extensive. Okay, that's what I would select. And moving on. Okay, another phase diagram. Let me actually take a screenshot. And just to remind ourselves again, okay, phase diagram has the boundaries between the phases. Okay, so for an example, we have the solid here, we have the liquid over here. At very low pressures and high temperatures, we have the gases over here. Okay, those are our phases, and then we have these boundaries indicated here. So this is the liquid gas boundary, and this is the solid liquid boundary. That's a bad arrow. Can I try? I'm going to try that again. Here, this is the solid liquid boundary, and then we also have this solid gas boundary over here. Okay. Anyway, so it's just a reminder about what we see in a phase diagram. So the question is one of the most common compounds used in dry cleaning industry. The phase diagram of this substance is shown to the right, shown below. What is the stable phase of PERC at 450 K and normal atmospheric pressure, 180 m. You know, normal is 180 m. Okay, so if we just try to mark them, so normal means 180 m, and then 450 is somewhere around here. So I would say we are around this region over here. Okay, clearly at 450 K and 180 m, it's in the gas phase. So we would select gas phase over here because this point is in the gas phase side. Okay, now let's select that. Moving on, question 8. That's our last question. Okay, let me take another screenshot and working with that. Okay, so again, we have the solid, liquid, gas. Okay, so that's the first thing I want to do when I see a phase diagram. Okay, so I just mark where my phases are: solid, liquid, and gas. Anyway, estimate the normal boiling point of the substance in degrees Celsius. Okay, now what we want to do is normal. Whenever you see the word normal, that means at 180 m. Okay, so whenever you see the word normal, what I would do is I would draw a line at 180 m. Okay, because we are dealing at that pressure. We are dealing with that pressure. Okay, that's what that means. And then boiling involves the liquid gas boundary. Okay, this boundary over here. And then 180 m touches that boundary around this point over here. So at that point, I would say the temperature is very closer to 400. I think it is between 395 or something like that. Let's say 400. Okay, let's say our Kelvin temperature is 400. Okay, so 400 Kelvin is equal to our conversion factors, if you can remember. The Celsius temperature is, let's say T Celsius plus 273 is 400. Therefore, Celsius temperature must be 400 minus 273. And this should be 127. Yeah, let's go with 127 degrees Celsius. Okay, now the closest one to 127 degrees Celsius is this answer over here, so we're gonna go with that, and we select that. Oh, that's the last question. Let's submit our quiz and let's see how we have done here. Submitted. There you go. That's how we get 100% on a quiz. All right. That's all. Bye, everybody.